I'll just begin with a brief introduction before we really start to talk. So my name is Dorst. I'm from the University of Amsterdam. I was always interested in geometrical puzzles. I've worked in robotics at Philips in the United States on path planning problems. There's Steve, and I saw him drop by. So I needed lots of tools I found to solve interesting geometrical puzzles, like the geometry of contact in robotics, how to stay clear of collisions. And I was working that out using mathematical morphology and Legendre transforms, and every time I needed a different book of math to resolve the next part of my problem, and I needed to invent a new representation, which already existed, but it was in a different book. And then in 1997 I attended a little workshop, which was algebraic frames for the perception action cycle. I gave a memorable demonstration with a Lego car driving over a overhead projector, because those were the days, of the Lie algebra of a car, of controlling a car. And there was a guy there, David Hestenes, who gave a brief talk, 3/4 of an hour, about something I'd never heard of, geometric algebra, and it completely changed my life. All these representations that I needed different math books for were present there, just in one formalism of a talk of 3/4 of an hour, which was introductory, which is precisely how I wanted geometry to be. You know, I had a simple geometric idea. Why was casting it in math so difficult? And so it changed my life. I hope I can do the same for you. And life will never be the same. You heard it here first. Okay, so the talk that I'm sort of reusing is one that I prepared for applied mathematicians in Brazil, in a national conference for applied mathematics. So I'm going to take a take that is more about the structure of geometric algebra more than immediately its programming, but I hope it helps you. And what I especially want to focus on is how geometric algebra, I'm assuming that you are used to doing geometrical things of a discrete nature, mostly with linear algebra, but how we can subsume, extend, invigorate linear algebra. Even if you never use geometric algebra, your linear algebra will become better if you know a little bit of geometric algebra. And the theme was sort of get real, which is a pun between, you know, wake up, and also that things that you are used to involving complex numbers and quaternions, yeah, they're just the ratios of real planes. You know, there is nothing complex about them. Yeah, they square to -1, but that's all. Okay, so what is typical if you want to solve a group of geometrical puzzles? Just a set of related puzzles like kinematics or dynamics or that kind of group of geometry. Well, you have to understand the geometric structure, which means the primitives, the objects that you have, their relationships, whether intersections, spanning, things like that, and the operators that you want to work with. You would ideally encode that algebraically, you know, the geometry then to the algebra, and then you use the algebra to good software, which is a consistent implementation without exceptions because you understood the algebra so well. So that'll give you your solution, hopefully, to the puzzle you had, like what is the inverse kinematic solution, and it also, ideally, would be used as a specification for the computational software. Nowhere in this do you need coordinates. It's only when you've written your program that your data comes in, which presumably is encoded with specific positions and so on, specific angles. You put those in, your program works with those incoming data. Well, that's not how we do it when we use linear algebra. There are basic primitives in linear algebra, the subspaces, which aren't really algebraic. We have the span of a bunch of vectors, we call that a subspace, but that's not a linear operator because the span doesn't change when you change these elements. There's sort of an algorithmic thing in there that if there's redundancy or linear dependence, then you should reduce that first before you actually can determine the span. So the subspace, which is a very basic concept in linear algebra because eigenspaces, vectors collect themselves naturally into subspaces, is actually not a part of the algebra itself. It's where you see little bits of English, column space, null space, span. You need coordinates even to specify the operators, because you have to choose a coordinate system in which you then say, well, the unit vector transforms to this, so that's the first column of my matrix. The coordinate system has nothing to do with the problem that you're actually solving. If you want to do operations like translation or so, it really depends on whether you translate a point or whether you translate a line or translate a plane. Your operators have to adapt themselves to the operation, the operand they're acting on. There are certain operators that we use quite a lot, like orthogonal transformations, that are actually hard in linear algebra because they're matrices with constraints. And so I always have to make sure that they don't move off the orthogonal transformations when I do an estimation. If you make a bug at the coordinate level, you produce nonsense. It's no longer geometry. You actually make a real mistake. It's very hard to spot where those things happen. And then when you really start doing it, you have seen this morning that the standard way is reverting to quaternions or biquaternions. So actually you leave your linear algebra because it wasn't good enough. This is not how it needs to be. We really want something like the first part. We want an algebra that can do geometry, only geometry, all of geometry, and it can be used both to state the problem, to solve the problem, and to implement the problem. And our claim of the presenters here in different stages of fields is that is the thing we have for that. I like to start with a little demonstration. So this is software that's freely downloadable. It actually comes with my book, but the website geometricalgebra.net or geometrica.org, I bought both of them, contains it as a freely downloadable thing. So each of the figures of the book, this is figure 1.1, so I typed figure 1.1 and you get figure 1 of the book. You can look at it from all directions. Okay, that's not so special. But each of the elements can also be manipulated. So what is going on here? There's 3 points that define a circle. That circle is rotating around this given line. That gives the green trajectory, which is maybe a little bit visible. Now I have a plane, and that plane reflects the line and all the rotated circles. So it's an artificial situation. It has a bit of a mathematical flavor, but and I can also change the angle of rotation by making it more or less. It's a simple geometrical situation, and you would really want at least the simple scene to be described by simple principles. I give a little teaser of how that's going to look like, and only at the end of the talk will we understand how that's put together. But it is possible to define a geometric algebra, because there is more than one, in which the circle through 3 points is just a wedge product, a special product that we have that spans subspaces. The rotation of the circle is the application of something we call a rotor. You can call it a biquaternion because it is a rotation not through the origin, but it is done by sandwiching, so r times c divided by r. Okay, but we have to make this rotation operation around the line, so let's look how a line is represented. Well, a line is just 2 points and a point at infinity, so it's a circle that passes through infinity, or 1 point and a direction and a point at infinity, which is also has a representation in the algebra. And then when I want to make the rotation around the line, I just take the exponent of the line with the angle I want, and that is my rotation operator that will rotate my circle. The plane representation, well, how have I specified the plane? I had a point on it and a normal vector, then this is what a plane does. And if I want to do the reflection of this line in that plane, or if anything in that plane, I just do again a sandwiching operation between the plane times the thing I want to reflect divided by the plane. And I have executed the motion here incrementally. That means I really don't want to do the whole rotation at once. I want to do it in n steps. Well, that's the nth root of this thing. Now you see, there are nowhere coordinates, right? I've completely parameterized this by how I know about the line. I had 2 points. Then how do I know that I want to rotate around the line? That's the exponent of the line. What do I rotate? I sandwich it, the thing I want to rotate, between the line and anything I can do that way. All of these are based on one product. It's a geometric product. These are just sort of an anti-symmetric part and a symmetric part of the two that we find handy in computation, so we pull that out a little bit because they correspond to the more classical ways of spanning subspaces. But it is just one geometric product. And so this whole program is written in this way. If you look at the code that implements what you just saw, then yeah, the formulas are here, and you can really just type them in that way if you have set up your software properly. So all of these operators are just corresponding one-to-one on the lines. It's a little bit of a language to get used to, but as soon as you know that you want to use something as a reflector, that you have to use it as sandwiching, you can just do that. And so it almost makes no sense to make a special bit of code that says, give me the line that is given by a point and a direction vector. You just do the wedge product and you have it. Writing that as a subroutine is just almost makes no sense. How would you have done that in linear algebra? Well, you would find it hard to construct a circle. You wouldn't transform the circle. You would make a circle from 3 points, and then if you want to rotate the circle, you would first rotate the points, and then, well, you have to make a circle again, right? Because you have no basic, and you probably wrote that code yourself or you downloaded it from the internet. The rotation, the translated rotation, well, you can do it by homogeneous coordinates, or I could have replaced this by biquaternions, popping out of linear algebra and using some strange alien framework on a 4-dimensional sphere in a complex dimensional space, etc., and not understanding what I'm doing. This at least is still comprehensible. I have a line. There are many different ways of representing lines. I could do a position vector and a direction vector, but they all behave differently. I could have set it up as the intersection of two planes, so some kind of a space, the null space of a matrix of which the rows are homogeneous coordinate vectors of the plane representation. If I'm very advanced, I use Plucker coordinates. The rotation around a line through the origin, well, I can at least represent that in a fairly coordinate-free way by Rodriguez formula. Yeah, that's only this thing. I still don't know how to do it outside the origin. Okay, biquaternions, right? Leave linear algebra. And so on. The plane reflection is also something, but if I want to reflect something other than a point, like a line, I would really have to convert this matrix to the corresponding line representation so I can represent the reflection of the line in a proper way. There's no such simple sandwiching. This is how people used to do it up till this afternoon, 4 o'clock. And now we're going to see how you should do it. And so linear algebra typically consists of having to specify your operators in coordinates that are moreover not related to the problem that you're actually trying to address. There was no origin, there was no natural directions in the problem that I just sketched you. It takes a different form if you use the same operator, the thing that I want to do reflection, I don't want to do rotation on something else. So that's the first teaser. The second teaser is I have a number of points in 3-dimensional space, and I want to find the best circle through it. Now this is obviously not linear algebra because circle is not a basic element in linear algebra. But again, this space in which circles are subspaces come to the rescue. I will give you some more details later, but what we have is what we call conformal geometric algebra. We find a rather simple form that actually gives an unbiased estimate of the distance of a point to a circle, to a sphere. We make a symmetric operator out of this. You can represent this as a matrix if you want. Then we solve the problem and we find that eigenvectors of this operator are really the things that I'm interested in. This gives an orthogonal eigenbasis of spheres for the data, and again, applying this wedge product gives you then the optimal circle. I did this, presented this at a company that does geometric data processing. And even though you're going to understand that this was developed in a geometric algebra, the whole code is just MATLAB without geometric algebra. We are going to have to do very strange things. We take a point and we make a vector out of it that has, okay, this is homogeneous coordinates with something else. We have to make that matrix of the mapping that I talked about as this thing. So this is where the data goes in, the data matrix goes in this format, and there's a weird matrix M involved. The eigen problem is now MATLAB. The intersection can be defined as yet another weird matrix, but at least it's a matrix, so I can implement it in linear algebra and therefore in MATLAB. And then I just have to unpeel the components and see which ones represent the radius of the circle and which the center of the circle. But all of this can be done without knowing geometric algebra. You can implement it just with MATLAB. You probably would not think of it without using GA. Now it turns out, so I did this as a little puzzle because I was interested in knowing what the solution was, not because I really had an application. It turns out that a lot of books have been written even about circle fitting in the plane, let alone circle fitting in space. Deep books, good books, very complicated books, because this is a complicated nonlinear problem. What it turns out is I've shown you, well, I've not shown you, I've bombarded you with the fact that I can formulate it in such a way that it just becomes an eigenproblem, which is standard linear algebra. So by taking the right representation, you don't have to throw away all you know about linear algebra. No, eigenvalues, SVD, least squares, it's all still important, but the power of this tool is becoming much extended because you can embed things in such a way that it becomes linear algebra. And it turns out that my first attempt to do this, no, I wouldn't say that it took just a day, but it certainly took less than a week and didn't take as long as it took this guy to write the book. It was as good as the best solution known in literature, which was only in 2D and mine was in 3D. That's not because I'm extremely smart, or at least that didn't matter here. It's because the way of handling problems with geometric algebra, having the right algebra for the problem, really empowers the practitioner. Something that you try as a first reasonable thing that is dictated by the structure of geometric algebra is, for the sort of problems that we try to deal with, often also a very good solution. And that's how it should be. You know, geometric algebra is geometry is too important to be left to mathematicians, we say. So it turns out that the CGA, conformal geometric algebra, we'll talk a little bit more about that, is a good one to know for these kinds of problems involving spheres, circles, etc. If you're more interested in planes or multiple reflections in planes, rigid body motions, then there's an algebra called PGA, which you'll hear more about during the sessions. There are different geometric algebras, and but you will be lucky with most of the problems that most of the geometries that you encounter already have been studied. The algebras are known, the implementations are known, and you can just use them. For instance, Stephen's Ganja coffee shop is that. So, the purpose is to give you a feeling of how this works, why this works, that it's fun, but that there's some old things that you probably have to forget to actually absorb it completely. What turns out to be the procedure that we take is that if you have this target problem that lives in a certain geometry, a problem with circles and spheres and so on, that has certain primitives like translations and certain combinations of primitives like intersection of a line with a circle gives me a point pair, primitives, combinations and motions, we're always going to try and play the trick in which we lift it to the correct geometric algebra, in which everything takes place around an origin in a representational space. Every motion becomes a rotation, a rotor, a versor, a spinor. We'll have different names for that, but that's what it is. And every object is a subspace of a certain dimension, and the interaction of subspaces are the meets and the intersections of these subspaces. So set up a a one-to-one correspondence, or one-to-many, but where the primitives become subspaces, which we represent by certain computational elements, the combinations become certain products, and the motions always become orthogonal transformations in that space. And this has been played for a number of things. We're going to study for you in some detail the algebra of three-dimensional directions. We have seen a little bit this morning about the three-dimensional motions that leads to PGA, Projective Geometric Algebra. I showed you an example where we were talking about circles. Well, that turns out to be the algebra in which conformal geometry becomes orthogonal transformations. I'll give you a little bit more detail on that. And there's a number of other ones that have already been found. But this is the game we play. So you adapt your algebra to the geometry of your problem in such a way that your motions become spinors, exponentials of bivectors, rotations in that space, and your primitives will automatically become subspaces in that space. So let's take one of them, and that is sort of the model, the simplest model that you could have. So we're not going to talk about positions, but only about orientations, directions in a three-dimensional space. So we have an origin, and we have maybe some axes, maybe not. These axes are just directions. We have two-dimensional directions, planes going through the origin, maybe spanned by one-dimensional directions. We have intersections of these planes, which is again a direction, and we want to see what the algebra is behind these things. So for now, we stay at the origin, because it's the cleanest thing, and also because in the general mapping, this is actually sort of what we always achieve. So if we have the right mapping, we will always be at the origin of some kind of an algebra. You know that from homogeneous coordinates. No? It's very reminiscent of that. Subspaces are crucial primitives, but I already said they're not really computational elements of linear algebra. Even the fact that something is linearly independent is not a quantitative property, it's a binary Boolean property. You don't want that in geometry. We're going to use this to illustrate, and I think I made these points, and we will see that quaternions pop up quite naturally as the ratio of two planes. And the whole purpose here is to make algebra geometric again. I have some red hats that I can sell you that have that as a logo. MAGA. Okay, let's span subspaces. This is something that is pretty old. It's known as a Grassmann algebra in mathematics, but it hasn't really penetrated to core linear algebra teaching, even though subspaces are what linear algebra is about. What are we going to do? We're going to define an outer product, A wedge B, and we're going to say that A wedge B is minus B wedge A. So I have a vector A and a vector B, and they together span sort of a directed planar element. And if I would take them in the opposite direction, I would say that the planar element is the opposite direction. Right? This encodes linear dependence in a quantitative manner, I should say. One of the consequences is that A wedge A equals 0. So it's not quite like the span, because if I span a vector with itself, that vector, here it has to be 0, because I get something positive here, and now it's negative, so it has to be 0 in between, because we want to be linear. And indeed, this property, if I have another vector x that is part of such a wedge thing, then I can say that x is in the span of these vectors. That's the correspondence to the classical linear algebra. Why is that? Well, if it is in the span, I can write it as the sum of two, of A1 and A2. And if I then do the wedge product, then I develop all this. The wedge product is associative, distributive, linear in its arguments, etc. Everything you want it to be, because we're still setting up something linear. And then you see that I get these terms A1 wedge A1 and A2 wedge A2, and these are 0. So it disappears. But I can also be almost linearly dependent. You know, if I have a plane of spanned by two vectors and I have a vector that's not quite in the plane, then this will be, because of the linearity, just a small something that becomes only 0 when I'm in it, and a small negative something when I'm out of it again. So this is already an improvement over regular linear algebra. I'm beginning to have subspaces as elements of computation. And yeah, so we had vectors. We see them as denoting directions, any multiple of this thing. We have something that we'll see is not quite a vector, but is indeed like a two-dimensional area element. If we take 3, we get volumes, and if we take no element, just a scalar, then we get a weighted point at the origin, a zero-dimensional thing. How do I know what it represents? Well, let's do something weird. Let's introduce coordinates. You probably still think that's normal, but we don't. But it conveys the thought quite clearly. So I take a orthonormal basis E1, E2 in the plane of these vectors. And then I should be able to write the first vector as cosine plus sine and the second vector as cosine plus sine. I now use just the rules that I had for the wedge product. You know, I expand it, it's linear, distributive, etc. I get this element, which is 0. I get this element, which is 0. I get E1, E2, but that was minus E2, E1, so I can group these. And now I use my trigonometry to show that, oh, it's only the relative angle that matters. That's good, because these vectors were chosen relative to an arbitrary coordinate system, so if it's truly geometrical, I should have no relationship with the coordinate system at all. It's the relative angle, and I get something like this. And this thing, E1 wedge E2, well, that was the plane that those two things lay in. Let's not write it as E1 wedge E2, because if I rotate two of these vectors, it's still the same plane, so let's just call that I. And now I see that my element that I made with the wedge contains quantitative aspects about how big the vectors are. It contains angular aspects about how much aligned they are, and it contains spatial aspects of what plane they reside in. So this is a really nice thing to have. And these are going to play the role of subspaces. So this is with 2, with 3 you get similar things, in other dimensions you get more things. If you now look at what you can make with that wedge product, then you can build up a basis for any element that you're likely to get. You can get a scalar, you can get the vectors, and in 2D you can also make E1 wedge E2, which is the plane that you happen to be in. And now if you wedge any of these vectors with this, it becomes 0. Right? So it automatically closes, and this is all I get. In 3D, I have 3 vectors, so I will get more of these planar elements, coordinate planes in this case, because I took coordinate vectors, and I get a volume element over here. And now we see a little bit how geometric algebra, or, well, we're not in geometric algebra yet, we're still in Grassmann algebra, how this extends our vocabulary to deal with elements. So we usually talk about vectors when we talk about linear algebra. We also talk about complex numbers as combination of a scalar with something that squares to -1. A multiple of something that squares to -1. Well, I'll show you very soon that this thing actually squares to -1. So we also have complex numbers. So why are rotations nicely in a plane nicely represented by complex numbers? Because the plane itself is a rotation operator. It is a thing that can help you in the exponential map that you heard about this morning to build rotation operators. In 3D, what happens? Well, this is what I had, vectors. I've also used determinants, and it turns out they're related to volumes, so I've had those in the past. In 3D, I also found it handy to talk about normal vectors. Well, we don't. We actually find it handier to talk about the direct characterization of the plane, but these are sort of the normal vectors. But the combination of this and this, these also square all to -1, these are the quaternions. So even though I'm at the origin and I'm only talking about subspaces, we'll very soon see that if you want to make subspaces of any dimension, and you do naturally in linear algebra, then these are going to organize themselves in relationships that for free, in your linear algebra approach of subspaces, give you something that you recognize in hindsight 2020 hindsight, which is how Stephen actually wanted to call this gathering in hindsight, organize themselves as the quaternions, and we'll see biquaternions in other spaces. And so operators, things that we're used to thinking of as operators and things that we're used to thinking of as elements, are somehow all together in something that to you maybe now still looks like a bit of a salad, which is taken from the title from Charles Gunn's talk on Friday. But we have to give more structure. The Grassmann algebra doesn't quite have that yet, so now we're going to talk about the size of elements. You saw this morning that reflection may be an important operation to organize our operators. Let's look at that classically. So I have here a plane, and I have, maybe I should do the demo first. What is it? Figure 7.1. So that is from my book, Chapter 7, Figure 1. And there it is. So we can look at this a bit in 3D so you see better what's going on. So this is that plane with a normal vector A. I can change that normal vector. I'm taking a vector x, and I want to do something. I want to reflect this vector in that plane. Well, what do you do classically? You project this vector onto the normal vector, and then, if you take this vector, you get the reflection in the line. So this is x plus twice that, and if you take x minus twice that, you get over here. Right? So this projection plays an important role there in this. So it's a bit of a complicated operator, but you already see that in geometric algebra it's going to be rather simpler. So classically, we would say reflection is take the vector x, take minus 2x dot a times a divided by a squared. This is the classical projection operator, which I subtract twice from the vector to get this. Obviously not something very elementary, a reflection in a plane. It looks too complicated to be a sensible thing. One idea we could have is that this thing is symmetrical. Why would you have a symmetrical product? That's too much of a demand on a product. Let's say that it's only symmetrical because it is the symmetrical part of a much deeper product. XA plus AX divided by 2 is something that is clearly symmetrical in A and X. So let's replace the dot product, which we know, love, by this deeper product. Well, as you do that and you put that in this equation, you see that the 2 disappears and I get this. I hope that this product is such that I can multiply things out, so I get xa squared divided by a squared, and then I get another term minus axa divided by a squared. Wait a minute, a squared divided by the norm of a squared. Well, why not I set this new product in such a way that the square under this new product is equal to a dot a, the norm that I already have. Then this term disappears, this term disappears, this term disappears. All I'm left with is this. And then this a divided by a squared, well, if I dot that with itself, then I get 1. So this is sort of like the inverse of a vector. Right? It's actually that inverse of the vector. Right? You have a vector, you reflect it in a sphere, and you get 1 over the vector. Same direction, different magnitude. Oh, but now I get a much simpler expression for something that was a reflection. Here I would not think of using this as a basic building block for anything. Now I'm almost back in Lego, These are just, I have a vector, I have a plane, and what do I have to do to reflect the vector in the plane? I just sandwich it with the plane in front and the plane in the back. If the plane is a unit plane, so that a squared equals 0, then this element is the same as that. There's a little minus sign because I'm reflecting in the normal vector rather than in the line, but it certainly takes a simple expression. So by doing this trick of saying there is a deeper product of which the dot product is only the symmetrical part, I can get a much simplified thing. And if I want this to be true, I see that I have to assume certain properties of that product. I have to assume linearity, associativity. I have to assume that a squared equals a dot a. So wanting this to be true dictates the mathematics that comes out of this. Well, this is the geometric product, the basis of geometric algebra. It's also called the Clifford product because he thought of it first, but we think it's so important. And he's dead anyway. He died tragically early, otherwise we would have used this instead of linear algebra, because this was before linear algebra. This was before matrices. Okay, so we have a reflection in a plane. Let's do two reflections in a plane. Well, you've seen this morning that two reflections in a plane, we suspect that that might be a rotation. If I do two reflections on a plane, I have this operation, and now sandwiched with the second plane, all at the origin. Well, I can clearly, or the minus signs cancel, I can organize this, and if I look at the inverse of a product, then it's the product of the inverses in opposite order, right? As I always tell my students, if you put on your socks and then you put on your shoes, and you want to go back to barefoot, you first have to take your shoes off, and then you take your socks off, right? This is something they learn in my linear algebra class, and they'll never forget. And we have the feeling that it rotates over twice the angle. Well, maybe we should show that as well for the people who weren't here this morning. That, you know, I show it in two ways. This is sort of more easily visualized if you do the reflection in a line, and because the signs cancel, that doesn't matter that much anyway. So here I have a vector x, arbitrary vector x, and a plane spanned by A and B. I do first a reflection in A, and then I do a reflection in B. And then if I look from above, then I see that I have actually rotated over, and now I'll just manipulate A and B a little bit. You see that I've actually rotated over twice the angle between A and B. So this product of two vectors, this geometric product of two vectors, acts like a rotation operation on any kind of an element. You know, it doesn't matter where I am, and it doesn't matter what I do with A and B. The figure just is always a rotation in the plane spanned by A and B. Oh, that's nice. You know, we always wanted those. So this is a rotation operation. We are going to do a lot of these concatenations of geometric products of vectors used in a sandwiching product. So we're going to give it a name. We call it cursor. You can also normalize them, because obviously the inversion was in the same direction but divided by the square of the length, and if they're all units, then I just have to change the order, and that's good enough. If you do that, you call it a rotor, or if you're a physicist, you call it a spinor. But this is a real element, which is the multiplication of two planes under the geometric product to be applied in sandwiching to produce a rotation. It's also quaternion, which is rather unexpected in this context, but this is what quaternions do. They rotate in 3D over twice the angle of whatever I put in there, so it must be a quaternion. How can it be a quaternion? Well, we'll have to show that how that relates. And then we get into Cartan-Dieudonné, which was mentioned this morning, that a reflection is an orthogonal transformation, right? It preserves distances in the space that I do it on, a reflection to the origin. Cartan-Dieudonné tells us that if we're in an n-dimensional space and we want to make all orthogonal transformations, we can always make those with at most n reflections. Now, if you're in linear algebra formalism, then you would not use this as a fundamental representation to represent arbitrary orthogonal transformations. It's just not nice. But we've seen that if you have it in sandwich form, you easily concatenate them and split off the elements that actually perform the operation, and they become elements of the algebra by themselves. And now, suddenly, Cartan-Dieudonné, which was more of a mathematical curiosity, becomes a possibly fundamental way of representing your motions. And that's the game that we're playing when I said we have these two layers. We have your own algebra or geometry situation. We're going to embed it into a suitable geometric algebra. Well, we're going to play the game that we always try to pick a geometric algebra so that the motions you're interested in are orthogonal transformations in their representational space, because we have a good representation of orthogonal transformations. Again, this is something you wouldn't do necessarily in linear algebra, because you don't have a good representation of orthogonal transformations. They are heavily constrained matrices. You'd rather not have that. We do, so for us it becomes a goal. And just to look ahead, we did all this in the origin, or to look backwards, because Steven has already talked about this. If you would now want something that does Euclidean motions in 3D, then you would naturally want an algebra in which your basic elements, your vectors, are planes, because if I do a double reflection in a plane that is two planes that are parallel, I get a translation. If I do a reflection in two planes that have a common line, then I actually get a rotation around that line, which is the example I just showed, where the origin was still here. So you are looking for an algebra in which generally situated planes are the basic elements, the vectors. Okay, well, we have that. It's called PGA, and Charles drew our attention to its existence a long time ago, and we're finally beginning to recognize what he was saying. But if you have other things, spheres as vectors, then you build up things through multiple reflections in spheres, and that is one of the ways in which to represent conformal motion, so you get conformal geometric algebra. If you do it with lines, you get projective geometry, and so on. So the game can be played. I gave this presentation in Brazil, where they hadn't seen The Sound of Music, so a lot of my jokes bombed, but that's why I came to Belgium. I say let's start at the very beginning, and we could all sing it. We begin with ABC because they're the first vectors, right? But actually, we have already started at the beginning. What I just said was geometrically the beginning, and now we're going to, this was for applied mathematicians, to mathematically how you would do it. Mathematically, you would just say, hey, I have a product. Let's define a product with these properties, and let's see what it generates. We don't care whether it's useful or not, because we're mathematicians. But it's a nice structure, so let's study it. Well, we've seen where the rules come from, right? I want to make reflection something that is a sandwiching product, and I found that in order to do that, I wanted to replace my dot product by something that has these properties, otherwise I couldn't do it. So obviously there's a reason for doing it this way, and this was an original Clifford reason, which if you bombard people with this, you don't see where it's coming from and why you would need it at all. Even this is something that mathematicians don't necessarily like. They much more would like it if I would say that a Clifford algebra is the quotient of a tensor algebra on the metric space VQ by the two-sided ideal of this. That the fact that it's tensor algebra means that it has such properties, and the fact that it's ideal means that whenever x times x occurs, I can replace it by the quadratic form that I've already defined on this metric space. This is very important because it means it exists. This apparently doesn't, but I'm not a mathematician. For us it exists because it helps. Okay, so let's look a little bit further at this. We know why we're doing it. We think we can use Cartan-Dieudonné to represent arbitrary transformations. So I've only defined that x dot y was xy plus yx divided by 2. So I'm going to find out, let's take an orthonormal basis again, because you all like coordinates until 4 o'clock this afternoon. And let's take E1 dot E2 dot E1. Well, obviously that's E1, E1 plus E1, E1. I already know what the answer is because I have defined a dot product. So this E1, E1 must be 1. So I have a vector that squares to 1. Okay? You may think that's not exceptional, but as you've seen in Steven's examples, we also like vectors that square to 0 or that square to -1. They all have their uses. So it's good to establish this. If we take E1 plus dot E2, we also know, because it was an orthonormal basis, that we want it to be 0. Okay, we write it in our language. Okay, but if this has to be equal to that, then we must have that E1, E2 equals minus E2, E1. just like the outer product already had, the geometric product between two different orthonormal vectors, or orthogonal vectors even, involves a minus sign. Alright, so now let's take a general vector, direction vector in 3D, and another one, and let's just use the rules that we have. Just do the administration. You wanted coordinates, you get coordinates. And I see that a lot of these things now group because of the E1.E1 and the E2.E2 and the E3.E3 all being equal to 1 to something that I recognize as the dot product. And because of the anti-symmetry, I get something with x1, y3, and I get something with y2, x3. And there will be a minus sign in between if I want to factor out the common, whatever this is. It's just obeying the rules. Okay, and this, well, we have a trick. If we multiply with E1, E2, E3, then this is not such a weird thing that has these things. If I multiply with E1, E2, E3 on this side, then the E1 and the E2 cancel because of the rules above. I'm left with the E3, so now I'm left with a vector that has these components. And in 3D, we happen to recognize this vector. It's a cross product. So, two things that we were already using, the dot product and the cross product in 3D, are unified or recognizable as parts of the geometric product. Well, that's very nice. We introduced the geometric product to make reflections easy, and we recognize some old friends, but together. And we also know that this product was defined to be invertible. You know, if I have xy and I multiply on the right with y inverse, which I had, then y times y inverse is 1, so I get x back. So by combining these two things, which I would never think of combining before, the dot product and the cross product, I get an invertible product. So I can divide by vectors. I can solve equations with vectors as if they were real numbers. I just have to be a little bit careful about commutativity, but I can divide out vectors. These other elements that we have here, I've earlier suggested that there might be complex numbers or quaternions or something in there. Well, let's now see that we indeed have E1, E2 squared equals what? Minus 1. E1, E2 squared is this, written out. It's associative, so I can put the brackets like this. I took an orthonormal basis, so I can use this rule and swap them, but I get a minus sign. I group them again, and now I can use this rule twice. And indeed, this thing, this planar element, this element that had the same properties as spanning two vectors, two orthogonal vectors, as squares to minus 1. So I have complex numbers, I have quaternions, but I haven't made them, and I don't have to say that they're complex. I can actually get real. Also in Brazil, that is as get real, which is their local money, and they did this talk, so they knew why I was there. So, but this is how complex numbers and so as soon as you admit subspaces and you admit the geometric product as a way of organizing the symmetry and the anti-symmetry in things, you automatically get complex numbers and quaternions without ever needing them and without having to take a class in complex numbers, because they're just elements of this thing. So we've seen the symmetric part gives the dot product. Well, it will hopefully not surprise you that if you take the anti-symmetric part, you get an anti-symmetric product which you can actually identify with the thing we had before. So we could have started just from the geometric product and said, oh, this is an interesting combination, let's see what it does. And this is an interesting combination, let's see what it does. But there is only one product. It's just that spanning and projection are natural things to want not to have to construct all the time like this. And if you now look at this earlier equation we had, yeah, well, we know that this is the norm of x times the norm of y times the cosine of the angle between them. And this is something like the norm of x times the norm of y times the sine of the angle between them. And this is then a spatial element that is attached. So the geometric product could also be written in a form in which I have b and a and the cosine and the sine. And I would be tempted to write this as the exponential of this bivector element in here, Why can I do that? Well, if I just define the exponential as expanding the Taylor series of the exponential, then the fact that this squares to -1 gives me the same reason as it works for complex numbers to be allowed to write this. Right? So this, I can write it in a product form of directions, or I can write it as saying, well, you were talking about this plane and you wanted to turn in it. Let's call I phi the bivector rotation angle. And if you really want the rotation operation, do the exponentiation. If you want to apply it, use the sandwiching. In general, when you expand this in a larger algebra and you have two arbitrary elements x and y of certain dimensionality, then you'll find that, yeah, if you're lucky, then none of them cancel with this double product, only E1, E1. There's no doubles in here, so you get something of the great dimensionality of x plus the dimensionality of a. But sometimes you don't, because you are only in a 5-dimensional space and you multiply something 3-dimensional by something 3-dimensional, and that will give this term 0. But pairs of things can cancel, so you can also get a term of this dimensionality, and so on, until you've exhausted the possibilities for things to cancel. In 3D, this was the dot product, this was the outer product, and there's nothing in between if you do it with vectors. In general, there may be other things. We haven't given them all names. We haven't learned to use them so well. All right. So, a bit more feeling of, one of the things that strikes people as really strange is that we dare to add something that is obviously a number to something that is, well, not a number, right? This was this E1 wedge E2, it's this bivector type element, plane-like element. Why is it really a plus? Well, you can see the invertibility of the geometric product from this figure. If I give you a vector and I give you the dot product of an unknown vector with that vector, do you know what the unknown vector is? No, we are here. I gave you the things of constant dot product are a plane perpendicular to this vector A, and I've only told you the value of that perpendicularity issue, but x could be anywhere on this plane. Well, this is actually the plane equation, right? Similarly, if I would tell you, well, maybe you should read it as the cross product, tell you the cross product of my known vector with the unknown vector, so I know the vector and I know the vector A and I know the cross product, then all the possibilities of x are on this line. Now, this is the thing that spans the same side of area with the vector x. Also not invertible. But if I have something that has both of them, then clearly the unique intersection of that line with the plane is where the vector x has to be, because it has to be on the plane and on the line. And you see that very clearly in the computation of the decomposition in using the geometric product. I can obviously write x as x times xa divided by a. I just put brackets around it, but a is invertible. I know that I can write this out as x dot a plus x by j, because I've just shown you. Oh, okay, but now if I divide it by a and it's distributive, then this is clearly recognizable as the projection. You know, take a unit vector, then this is x dot u divided, or times u. That's the projection. So this is the along part, and the other one must then be, we call it the rejection. It's the part of x that doesn't want to be, have nothing to do with a at all. Well, these are vectors. So if I take something that is of dimensionality null plus dimensionality 2, and I multiply or divide it by something of dimensionality 1, then I get something of the sum of the dimensions here and of the difference of the dimensions there. These are both vectors, and clearly I want this to be a plus. So let's make this a plus as well. It's all totally consistent, and this is decomposition not relative to a fixed basis that you had before, but a vector A that for some reason is important in your problem. In fact, the fact that it doesn't commute is very handy and very geometrical. It turns out for vectors that if two vectors commute, then they're parallel. Because it means x wedge A equals 0, so x doesn't span anything with A, so x must be along A. So this is true. The other one we've seen for the orthonormal basis is that if x and a anti-commute, if I change the order and get a minus sign, then the vectors are perpendicular. So very clear and useful geometric relationships between parallelness and perpendicularity, metric relationships. This one is metric, this actually not. It's Grassmann. This one is really geometric algebra. Are encoded in anti-commutativity of the product. Okay, and that works out more, except you get, in general dimensions, you have to bring this several times to the other side of this object A, which has dimension 2. So you get as many signs, minus signs, as A has factors. And so we have this little handy hat to indicate that. But again, parallelity, being parallel and being perpendicular are simple commutative relationships. And if we now look at that sandwiching product that we have, but we now don't do it with vectors, but really with one of those spinor-like elements, then this x can be, so let's say that r is the rotation in the I-plane, then I'm obviously going to be interested in with the components of x that are in the I-plane and that are outside the I-plane. There are, so this is the perpendicular component, this is the parallel component. Then there are different commutation rules for each of those. So one of them allows me to bring r to the other side. The perpendicular component doesn't feel the rotation. That is expressed as the fact that it's perpendicular to the rotation plane. So I can just rewrite r x perpendicular to x perpendicular r. And these things cancel, so this component is indeed not changed. If I look at the other one, then, well, if r goes to the other side of this one, if I goes to the other side of this one, it changes its sign. That means that the rotation operation over r becomes the inverse of the rotation operator. So now I get this. This I know I can write like that. And now I see that I have derived Rodriguez formula. If you are relative to a plane and you have a vector x, then the rotated version of vector x consists of 3 components. One of them is that the projection of x on the plane rotates by cosine phi. The perpendicular component doesn't change, and this one changes by sine phi. Well, these are precisely these components. Right, so Rodriguez formula, if you know it, is a precursor to the coordinate-free way of characterizing rotations. And a much easier way of talking about, you can make a matrix out of this as well, of course, because we just are rotating a vector x, so this is an operation that applies to a matrix, and that's how it's usually presented. But it is a good example of making an orthogonal coordinate system that matches your problem. You have a plane I, you have a vector x, okay, there's a little bit of this, the result is a little bit of this, cosine, a little bit of this, sine, and a little bit of this, 1. And that makes my rotation. And so this is coordinate-free rotation, but yeah, we already knew it, we just recognize it now. Okay, there are 2 ways of talking about spaces. So we have seen that if we have a A1, A2, and A3, I can span the space by taking the wedge product. So I represent the subspace by vectors in it. It is also, I could also say, well, if I have some span of things and I look at the vectors perpendicular to it, so the dot product is 0, then I have sort of represented it like what in linear algebra we would call this the column space, and we would call this the null space of B transpose, the things that are perpendicular to the rows. All right, that's handy to have. Well, the conversion between those two in geometric algebra is quite simple. The dual element, so going from this representation to that or from this representation to that, just involves dividing by the volume element of the space. This is E1, wedge E2, wedge E3, wedge E. So the two, if you divide by the volume of the space, you pop from something that's in the plane to something that's perpendicular to the plane, and not only for planes. And this gives an intimate relationship between these two products. You can actually define the dot product by saying that you want the dual of the span to be the dot product with the dual. So there's a very tight relationship there. So this is handy because it turns out that certain operations are actually handier to perform on one or the other of the two representations, but we have them both. And here's an example. I'm trying to work up to a next point to give you a bit of a break, so you can go somewhere with your joy. It turns out that when you work out this dot product and the wedge product, that the dot product of a wedge has this relationship. In cross product terminology, this is the back cap formula. But that means that if this is 0 and this is 0, then this is 0. Okay, so if I have something, if this represents x is on a plane, because x dot a equals 0, plane perpendicular to a, and this represents x is on the plane on b, then x must be on the line common to a and b. So then this interpretation being 0 would be x is on the line, so then this is the dual representation of the line. And that's how we can get, right? So by duality we can get an intersection operation that works on these elements, and we can now, when we go to conformal geometric algebra, you'll see that the circle that interacts two spheres is just the wedge of the two spheres in the dual representation. This can be defined in any geometric algebra. It doesn't really, I introduced it with dot and wedge, but actually the structure is already present in Grassmann algebra. So we get closure and we can make anything. I think I have a, yeah, okay, I'll stop there. What happens now with linear transformations? Well, we sort of already knew what happened with linear transformations. If you have two vectors x and y, and you have their sum, then we know that linear transformations are such that if I first transform fx and then I transform fy, that the sum of these two is just, can be made in either way. I either transform this or I make the sum in the image. That's a linearity property. But we interpret this figure in a second way. This sum involves completing the parallelogram. This is the wedge product, the span of the two things. So this figure also tells me that if I originally had something that was spanned by x and y, then the linear transformation will make it into something that is spanned by fx and fy. So I'm going to move up my linear transformations to act on arbitrary subspaces through the origin by just saying that f acting on this just means that, well, you could compute it by first doing f on each of the vectors and then doing the wedge product, or you could do it immediately. Either way it's consistent. And this is sort of, in linear algebra you would express that if you do a matrix on the column space of another matrix, then it becomes the column space of m times that matrix. It's sort of the same statement. So things that are handy. You can now do adjoints between arbitrary subspaces. You can get a closed form of the inverse of any of the subspaces, which is really handy when you have composite expressions and you want to see, if I change the subspace a little bit, what happens to the total computation. Projection becomes universal. If I want to project something on something else, it's always x dot a divided by a. In linear algebra, you have a similar formula that looks more like this, right? This is the projection formula onto the column space of A, but this is only for vectors. This one is for any kind of an element, also for other subspaces, for projection operators, etc. Yeah, if you let this act on the volume element of the space, then you get what it does on vector 1, wedge what it does on vector 2. You actually get that the volume element scales with the determinant. We know that in linear algebra. But now we can say that the volume is an eigen element of the operator with eigenvalue determinant f. So it just expands some of these notions a bit. Now, knowing this, that subspaces can be elements of computation and these operations exist, really already does something for how you look at the structure of linear algebra programs. Even if you don't use geometric algebra you now understand better what a linear operator is, because you have an extra tool to describe what it does. It's not only the linearity property of addition and scaling, the important spanning property, which is sort of implicit in linear algebra, but we've made explicit here. It's Grassmann algebra. Now, how would a composite element reflect? Now, it is a linear operator, so if I want to do a complex element, then I would reflect the first, I factorize it. I do the first factor, the second factor, the third factor, and so on. But now I see that obviously this cancels that, all these, and the only a's that remain are on the outside. So the reflection of x is just something like this, where the hat again indicates that if it's odd dimensional, you get a minus sign, and otherwise not. But now we have made these wedge products and these dot products out of linear combinations of geometric products. So if the geometric product transforms this way, then everything transforms that way. You never have to individually, remember that example that I gave of the circle, that in linear algebra you would, if you rotate a circle, you would have to rotate the 3 points that span the circle and then make the circle on the result. And then if you want to do it again, take another 3 points and do it. Obviously now we can just put the circle in there and it'll move with the whole thing. So this is the reason why the sandwiching, that one-sided product, is so important, is because in compositions you can, the subsequent elements just cancel and you can pull out the operator out of the whole thing. You won't be able to do that with a prefix notation of a matrix, not obviously. It becomes a lot more involved, and that's true because the matrix of how a matrix transforms a line is different how a matrix transforms a point. How a reflection here transforms a line is exactly the same as the way it transforms a point, because I can pull the operator out, and I have points and lines as basic elements. So this explains the prevalence of the sandwiching product, and this is why we like these orthogonal transformations. We have structures that are intersections, joins, 3 points joined form a circle in a certain way. And we want them to transform just with our basic motions. So obviously we want this property. We don't want to have to enforce it all the time. We don't want to have to check it all the time. We just want to make the algebra make this be true all the time. And this representation of motions as orthogonal transformations represented by these versors obviously has this property. So you have to write only one bit of code when you want to rotate something, and you can put anything in and rotate it. I'll give a little demonstration of that later. Okay, so yeah, I think you already got a little bit of the flavor of this get real theme, right? We have a real geometric algebra. If you would define it mathematically, you would say that our scalars are real numbers, the things that we multiply vectors by, and the other things are real numbers. And we don't seem to need complex numbers because we get them anyway. We have unit elements that square to -1, and they produce those rotations. There are people who, mathematicians like to generalize and they define a Clifford algebra over the complex numbers. There's absolutely no need to do that. You get the same thing a few dimensions lower, but you really stay real. A real plane squares to -1. Well, why? Yeah, because rotations, if you do rotations a number of times, you get back to the original thing. So that's why you expect things that square to -1 to play a role to reverse something, and a real plane does that. Okay, I have worked it out in some more detail. My experience is that this is a bit of a dense slide, but effectively, you saw it this morning, Turnians, so reflections of planes in the origin, they really are rotations. They are rotations over the half angle. And effectively, if you look at what happens in the quaternion product, now seen as a geometric product, that if I have a rotation in this plane over this angle, let's say a rotation over 90 degrees, so that's represented in this plane by an arc of 45 degrees, and I follow that by a rotation of 120 degrees in this plane. So that is represented by an arc of 60 degrees. And it turns out that the quaternion product works out in precisely the right way, so that the resulting rotation is now in this plane over the angle that I get by doubling the length of this arc. So this is addition of spherical arcs in space, which happens to be well represented by the quaternion product or by the geometric product. But you can visually combine rotations in this way, and it's not harder than combining translations, which is the same vector addition but then in a plane rather than on a sphere. So all these things are actually completely real. So don't go to say that quaternions live on a four-dimensional sphere or so. It's just not, it's not helpful. So the eigenspaces of rotations are real. Well, yeah, I should probably not show too many formulas, but the exponential of this thing can be written out as a bit of cosine and I times a bit of sine. And if I have a vector that is perpendicular to the plane, then the dot product is 0, so it commutes. So I am able to work this to the other way, so it's preserved. If I have the plane itself, then RIR, well, this is a scalar, this is I, and I times I is the same as reverse order, because that's I times I as well. So this also factors through, and so this is also preserved. So rather than saying a rotation has complex eigenvalues, we say that a rotation has a real axis, a one-dimensional vector, as eigenelement, and it has a two-dimensional element as IR, namely the rotation plane. If I then say, okay, let's look in more detail what it does in the rotation plane, so I take a vector that is in the plane, then I find that now I have this anti-commutative property, so now I can group these things together, and now I get something that looks very much like I'm multiplying this vector with a complex number, but the complex number is tied to the plane it's in. You know, the I is the physical I of the oriented plane in space. So we wouldn't say that this is a complex eigenvalue. We would say that within the eigenplane, it acts as a rotation operator with the power. Right? So, but the formulas look very, very similar to what you would do for complex numbers. There is an anti-commutativity which makes you a little bit more careful, but this is how we look at it. So everything is real. Something squared to -1. Okay, now we were going to go back to the more general motions just briefly, and then we would talk about two planes with a distance t over 2, t for 2 as it were. And if you then look at plane with normal vector E1, well, sorry, here is it, a plane with normal vector n and a plane a little bit further with that normal vector, then it turns out that the space in which you should represent this is something in which the are basis vectors. You know such a space, you know, homogeneous coordinates do that, but you're not used to having a geometric product in that space. Well, that's because the last added coordinate is a bit problematic. We saw this morning that there's a very good reason to make that square to 0 so that it doesn't bother you, and that's exactly precisely what you should do. And so this becomes a rotation operator, and this is actually the exponential of a direction. The exponential of a direction is an operator that moves you in that direction. If we do something similar with two planes that make an angle of phi over 2, then we get an operator. This looks very difficult, exponential of something. Well, it turns out that this I phi actually represents the line common to the planes. The angle phi over 2, I get in there, right? Here it is. And so in the initial example, I showed you something where I made a rotation operation by taking the exponential of a line. This is that construction. Yeah, okay. This squared to -1, yeah. That's why it's a rotation. But it's also a line. A dual line, actually, in one algebra, and if you have an algebra that already contains the duals as the natural elements, then it is a bivector. So geometrical elements can be made, can be exponentiated to make them a symmetry of the thing that preserves obviously that element itself. And that is what Stephen took at the basis of his talk this morning. So I started from making the subspaces and doing something with them. He started with the operators and seeing whether he could retrieve something in subspaces. And we saw that there were some questions about the signs. Well, they're more obviously present here when you do the bottom-up construction. But there are two legitimate views of the thing we're making. So all these orthogonal transformations, not all orthogonal transformations, but the transformations that contain an even number of reflections can all be written. They're part of a Lie algebra, you know, it's a lie. Lie, I mean, can all be represented as the exponential of a bivector to move them along. Well, if you can do the exponential, you can probably also define a logarithm. So if you need that nth root to do something in n steps rather than in one go, yeah, well, what would you do? You take the nth root of the thing. So if you have something like a rotation operator, you retrieve its bivector, you divide that in n pieces, and those are the basic operators that you apply n times to do this, and that's how that was constructed. It's not always easy to find a closed form formula for the logarithm in the algebras. I've done it for the conformal one, and in the PGA, the Euclidean motion algebra, it's actually really very simple. It's 1 plus the operator divided and then normalized. Sorry, that's a square root. I was momentarily distracted. Yeah, that's the square root. Yeah. Okay. Now we have now just done. You have the feeling that there's continuous motions in there, and that these bivectors are like a Lie. Well, they are. You can actually also develop a geometric calculus, so you can differentiate a geometric element relative to another geometric element. This is something that I find that it never becomes really easy, but it is possible, and you get vector calculus, but then generalized to other things. The interesting thing is that you do get extra tools that you didn't have before. So this is figure 8.3. Let's do a little demo again. Why not? So chapter 8.3. So here I have a vector x, and this vector x is normalized. That means that after I'm done normalizing, it lies on the unit sphere. Now I'm going to perturb my vector x. I'm going to perturb my vector x with a little vector a. That means that the result of normalization also changes. It's still a unit vector, but differentially, it moves a little bit in 3D over that sphere. What is that movement? Okay, so this is something that you could ask differential calculus to resolve, and it has some interesting properties that if your variation A is along the vector, then you don't see anything at all, then there is no change, and you should of course not go too far away because we do first order approximations. Yeah, well, that is precisely the result that you get, but you can use the geometric algebra operators to actually, if you do this differentiation by the rules, for which I always have to consult a table, then you can group the elements that you get in a form where here again we recognize something that a wedge x divided by x. This is actually the rejection of a by x. That is the component of this vector a that is most unlike x. Okay, that's exactly the perpendicular. That's exactly what you would expect. Now classically you would probably have written it as x minus the projection on it, but we have a more compact way of talking about that now. But it all works. You even, if you do differentiation with respect to a vector, then that itself is an element of the algebra, and it is related to a vector. It's actually a dimensional one object. That means I really have to be very careful. Oh, I didn't say that on the previous one. I cannot move the differentiation operation just through the things it differentiates, because I'm not allowed to switch this element and that element without being punished. So now we need a bit of a special notation. Here the differentiation acts on A. Here the differentiation, its geometrical aspects are still here, but it acts on B. And if you do that carefully, then you get something consistent. The nice thing is now that if we look at this, we recognize this as a geometric product of a vector with something else. Okay, that's a dot product plus a wedge product. So it has a part which is the dot product of the differentiation, and something that, well, let's stay in I3, so in 3 dimensions, then we can rewrite the wedge product as dual to the cross product. So this is the diff and that's the curl. One differentiation contains both the diff and the curl. Geometric multiplication is invertible, so the result of the differentiation is invertible, integrable, in principle, if you really have to need both components. And integration is just the inverse of differentiation. Well, okay, it gets a bit hairy to do it properly. But this is one of the reasons why there are no longer the Maxwell equations. There's only one Maxwell equation. We group what you classically can also do in one field, the electromagnetic field, which is now a bivector, because we have bivectors, and it turns out to be to express their transformation properties. And then you would still classically have two things for the diff and the curl. Yeah, but diff and the curl are just 2 aspects of one differentiation operator. So there's only one Maxwell equation, which is of course what you would expect. Why would there be a coupled set of equations? That means your algebra is wrong. And that's indeed what's happening, and that actually makes it easier to integrate the electromagnetic field equations, because you have everything organized in precisely the way it should be organized. Geometric calculus, interpolation and extrapolation. Yeah, if I have an object and I do a very small perturbation, then and the object changes more or less like this, and this is precisely this is a cross product now in geometric algebra. This is an anti-symmetric product between bivectors, commutator product. This is the product of Lie algebra. Lie algebra is the algebra of bivectors. You don't need to go to a separate chapter. It's in there. You have bivectors, you have the geometric product. They organize themselves because of the sandwiching naturally into this commutator product, and so that's why Lie algebras and commutator products are related. And now you can do more involved things to play with first order approximations of the bivector, actually giving you second order approximations to the orbit. But there's other stories I want to tell, so I'll stop there. Okay, in the original example I showed you this thing of circles apparently being elementary and being composed of points. And I even showed you, I don't know whether I have the slide here, that C1, wedge C2, wedge C3 was the circle. So apparently I can design an algebra in which points are represented by vectors, and in which if I span the volume of 3 vectors, I get a 3-dimensional subspace of that algebra that I can actually interpret as a circle. In the sense that a 4th point, when are you on this thing, x wedge, this thing is 0, I get precisely that the points that satisfy that are the points on the circle. This is how that's part of how that game is being played. So this is one of the successful examples of casting something into geometric algebra. It will give you Euclidean transformations on circles and so on, but it gives you something, conformal transformations. If you are only interested in Euclidean transformations and you don't necessarily circles as elementary elements, then there is a slightly simpler algebra, 1 dimension lower, the PGA, the algebra of plane-based geometric algebra. But let's go to this one. So let's do a design of an algebra that tries to fit the problem. Let's say that we're interested in Euclidean geometry and we now define that as that we want to have distance-preserving transformations. Well, we want to go to orthogonal transformations because we are good in representing those. So let's try to make the dot product represent this distance. Because then if I have transformations that preserve the dot product, the orthogonal transformations, then they preserve this, and therefore they are the transformations I'm interested in. Right? That's one of the ways to do it. The other way is to be like Steven and say Euclidean motions I make by multiple reflections in planes. This is another angle. Sometimes one gets you to the... it's still cancelling out, right? For the people at home, you should have been here. So how will we do that? So we have to embed Euclidean locations, x and y, in some kind of an algebra so that they're representatives. Note the difference in fonts. The dot product should be y. Now, we work this out and we see that we're going to need squares. Because, I'm doing a trick. This is a square root. I don't like square roots. There's never going to be really very linear. So let's take the square of this thing and try to represent that as a dot product. You know, little concession. Okay, I'm going to need squares. Well, that's non-linear in x and y. The dot product is linear in the representatives. So I have to put the squares in the representation. Right, so I get this as a representation. Okay, I try by Euclidean dot product between vectors like this. And now I get terms like this. Okay, I want those. No, I don't want those. So I'm certainly going to cancel them by setting this thing squared to 0. But now I'm in danger of losing this thing completely. I introduce yet another vector, n0. So I'm now, for a 3-dimensional space of Euclidean things, I'm up 2 dimensions because I had to introduce this n infinity and this n origin. I don't want that to interfere either, and now I've made something that looks like this. And if I now take the dot product between this, then I get this times this equals 0, this times this equals 0. So it doesn't bother me. I do keep this dot this, and I am going to define this very carefully in this manner so that if I do this and I do that, I precisely get the squared terms. I now group them, and yeah, I've sort of succeeded. You know, I've made an embedding in a space of 2 dimensions more, where I have to use Euclidean vector plus an n0 component plus an infinity component that contains x squares. It's a representation. And if I do the dot product in this space, I get the Euclidean distance. So if I now completely do transformations that preserve the dot product, I should have Euclidean transformations as orthogonal transformations, which I can represent with exponentials, etc. So this is the design strategy. I must have made a weird space. If I look at the table, then x dot x, I know, that's just the norm of x squared. But this is 0, this is -1, this is -1, and this is 0. I don't recognize this space. Okay, I can make a little transformation of basis, you know, introduce a new basis. See if that diagonalizes this metric. And now I see, okay, the unit vector squared are equal to 1, so this is 1, 1, 1. And there is an e plus and an e minus. Okay, I have a Minkowski space. I have a space with n plus 1 dimensions that square to 1, and 1 dimension that squares to -1. In the Minkowski space, I have all vectors. That is vectors of length that are not 0, but that have length 0. Yeah, well, I can see what null vectors would be, right? These were points. The distance of a point with itself is 0, so x dot x equals 0 for a point. I could have expected null vectors. Natural that I'm in a Minkowski space. It must happen. Okay, what other things are in there? So we have the points, which square to 0. They're null vectors. Any point. We can also make elements of this thing, a point and a bit of infinity. And if I now ask, when is x dot such an element equals 0, that I find that I can rewrite this. X dot c is the distance squared. I can rewrite this to this equation. So this is a circle with center point c and with radius rho. Okay, so spheres are vectors. If I have a plane and I resolve the same equation, of asking when a point has a dot product of 0 with this element, then I find that that's a plane. So this is a space in which the basis vectors are points, planes, and spheres. Okay, I'm going to do Stephen's trick. I'm going to use those vectors as the basic thing to do my reflections. I'm happy to see that I have the planes, because that means if I put the planes in parallel, I get a translation. If I put the planes intersecting, I get rotation. So I wanted all that. But I also get this spherical reflection. So I must have more than the Euclidean transformations. Yeah, that's true. I get conformal. I can either learn to be happy with that, or I should maybe go to a smaller space, which is PGA, if you own. But then you lose the round elements, the circles and spheres as bases. I'm going to play the game. You know, I have basis vectors. I can wedge them together. I can, with X wedge something, I can ask, well, what are you representing? X wedge is 0. Is what subspace are you? X dot, what dual subspace are you? I can answer all these questions, and I get a complete vocabulary of things that I totally recognize as elements of Euclidean geometry. I get spheres as the wedge of 4 points, circles as the wedge of 3 points, point pairs, that's if I intersect a circle and a sphere, I get a point pair, so a point pair is to be part of that. It's a one-dimensional circle, as it were. I get the flat elements, so the line in the beginning demo I said that if I have 2 points, a wedge infinity, then it becomes a straight circle, which we'd rather call a line, so I have those as well. I get directional elements. These are, turns out to be the translation invariant. They just indicate Euclidean directions. So that earlier algebra that I showed you, directions at a certain origin, yeah, the algebra of directions is a sub-algebra. And I even get tangents. This is rather interesting. If I have two spheres, 2 circles, then they have a point in common when I intersect them. They have no point in common. Okay, they have they have a point pair in common when I intersect them. They turn out to have an imaginary, or a point pair that squares to -1, I should say, in common when I pull them apart. But when they're just tangent, they don't have a point in common. They actually have a tangent element in common. They have a point in the direction in common. Tangent elements we are used to associating with differentiation. No, they're just the closure of the intersection operation. They're naturally present. They're elements that happen to square to 0, but they're naturally present as closure in a real algebra. Blah, blah, blah. Yeah, get real. I should get real too. Very nice things happen. I can represent a sphere as the wedge of 4 points. Or maybe I should. Yeah, maybe I'll make one just to convince you that this happens. So, probably, yeah, CLF. No, I'm in caps. Don't try this at home. I'm still in caps. CLF. So, how do I define points? Well, you know, I have that special vector NO, which is the point at the origin. Let's just take that. Oh, there's another script a bit active. Let me do this. A equals B. My daughter is taking a typing course, I'm not. And let's label the points so that we know what we're talking about. Label C. You can try this at home because you can download the software. Label D. Right. Now, these points were at the origin, but I have translations in my algebra, so I can just move them out of the origin. He knows how to do that. And now what I want to make is something that changes as a scene that changes with the points. So let's, in this language of this thing, you have to say that it's a scene. And I think I'm going to make a sphere by A, wedge, B, wedge, C, wedge, D. Okay. Ooh, it's not a sphere, it's a plane. Why is that? Because I initially drew these points out of the origin in the plane of my screen, so it won't be anything more. But as soon as I pull one of those points out, you see that actually it is a sphere. No? And no matter how I draw these points, I can always immediately compute the sphere in these things. If I had only taken 3 of them, I expect that I might get a circle. And this is true, except I redefined C, which wasn't very smart. Okay. Well, we just put C back in, and there it is. Put it at the origin. And so now I have a circle on a sphere, because obviously the 3 wedges of these things are that. So what is behind this is just something that computes the wedge product, and of course a display routine that knows if this is the wedge product and this is the center of the circle and so on. But if you want to find the center of a sphere, then for instance what you can do is you can take the point at infinity and reflect it in the sphere, and that gives you the center. There it is. Because if you do such a reflection, then that's one way of finding the center. If you want to know what the radius of the sphere is, you just square the sphere. That gives you a scalar number that is actually the radius. So all these things that are not hard at all, they are just part of the properly organized algebra. And I'm going through a bit of a computation here where I say that if you have the join of 2 points, then because of the anti-symmetric properties, I can just subtract a from each of them, because a wedge a equals 0 anyway. This actually turns out to be, if you take x dot with something like this, you're asking where are the points of which the distance is equal, set that to 0, where is the distance equal to a and to b, so that's a midplane. So this is a midplane between 2 of these points. This is the wedge of dual midplanes, that's a meet of 3 midplanes. The meet of where do 3 planes meet? Well, they meet in 2 points. They meet in the actual point that we're used to, plus they meet at the point at infinity, because all planes contain the point at infinity. So we call that a flat point. And you do some rewriting, and you now find that what you get is a representation of the sphere. This sphere I made with 4 points. This sphere is the midpoint and the radius. One is just exactly dual to the other. So if you implement it on a basis, you make this wedge product, and on the basis you can immediately read out, oh, this is the center and this is the radius. There's no complicated computation to convert from specify something by points to specifying something by center and radius. It's the same thing, just a dual. This is how things are organized. Now you begin maybe to see how I did that that sphere estimation thing. We now can understand that spheres could be elements of computation. We understand that a dot product of a point with a sphere, or this is the projection of a point on a sphere squared. Okay, that's probably something like a squared distance. If I sum that over all the points, then by these new operators I can make a symmetric map out of that. A symmetric map has an eigenbase, orthogonal eigenbases of spheres. Spheres are vectors, right? This is just linear algebra now. I am in a space in which I have a symmetric map, and I'm asking for the orthogonal eigenbases, except that the eigenbase consists of vectors, and I know those vectors are spheres. So I get the best fitting sphere, the next best fitting sphere that's perpendicular to that, the next best fitting sphere that's perpendicular to that, because the dot product between 2 spheres means that the spheres intersect orthogonally. I didn't say that, but you can work that out. So the best circle is just the intersection of the 2 best fitting spheres, the 2 eigenvectors. And that's what this software did. Here you see that representation where I represent the square of the thing as well. Here you see that metric matrix that I talked about for these 2 extra components with the -1 and the -1. Now it's an eigenproblem. Okay, I still want to provide the service that I want to compute this wedge product. That's not in my MATLAB, but it's a linear operation. If I keep this one fixed, then I make a linear thing out of this. So there must be a matrix, and I worked out what the matrix was if you have a point at y and a point at x. This matrix applies to that. And then you are in one of the center, and actually also the plane that it resides in. Yeah, so this was, once you have in the right, once you're in the right algebra, this is completely standard. These parts are completely standard linear algebra, and this is maybe something you wouldn't have thought of, but and maybe this not either. But all of it can just be implemented in MATLAB, and you can sort of see where it's coming from. Okay, now for the afterwards, I have lots of demos of interesting things that you can also do, because when I wrote the book, the Conformal group was rather new, so I went overboard and have been overboard ever since. I'm coming back on board now to the PGA. You can do different metrics without, you just change what you mean by the point at infinity. If the point at infinity squares to 0, you get Euclidean geometry. If it squares to +1, you get hyperbolic geometry. If it squares to -1, you get, and you don't have to change your program. You just change the vector that represents the point at infinity, and everything happens. I can do that demo later if people are interested. Now, this thing becomes big, right? The circle fitting shows that we can use the Bastille techniques we have developed for linear algebra just get a very large, much larger scope, because in the space that we have defined, interpreted back to our task, they get a different meaning. You wouldn't be able to do circle fitting in 3D with just regular linear algebra, but it is linear algebra in that space. So I'm not telling you to forget your linear algebra. I'm just don't do coordinates, don't do matrices. Use the versors and the spinors to represent your transformations. Once you have decided that this n-dimensional algebra is the place to be, so for the conformal model of 3D, this was 5-dimensional, you do have the whole list of subspaces, which is 2 to the n. So that's a 32-dimensional algebra, or if you stay modest, then you take the 3D with PGA, you still have a 16-dimensional algebra. So you really should be a little bit careful with implementing this, and not define matrices over this algebra, or think that any linear combination of these elements is something that can occur. You'll find out, of course, that in the end you're doing very much similar computations like you did in linear algebra anyway. When you give the thing points with coordinates, it'll multiply, it'll make combinations of coordinates. It doesn't do anything magical. So that means you could let the compiler take care of the most occurring products. If you do a lot of wedge products of 2 terms, let the compiler generate code for it. This is the stuff that you used to have to write by hand in coordinates with linear algebra. The compiler can use the geometric algebra structure to generate exactly that same code, but the compiler does it. It's not you doing it, and it will always be geometrical. Not that you have a minus sign wrong and it doesn't mean anything anymore. So that means that you now have high-level programming of GA available, and I showed you at the beginning that with that example that the formulas in the code are just very, very similar. You have a general projection operator, it's x dot a divided by a. You're not going to a function for that, you're just going to type in x dot a divided by a, because that's a projection operator, whatever x and a are. So your code becomes a lot more readable because they're not self-defined function names in there. Actually, if you look at what it does, then it's sort of the administration, the difference between directions and points, and they're all vectors, but they transform differently and so on. They all transform automatically correctly when they're embedded in this algebra, because things become 0 because they are part of, you know, a null vector factor. And so if you multiply these things with themselves, they cancel. This all happens automatically. So all the things that you had to do as sort of a Boolean administration of the types of, is it a direction vector, a position vector, is it a normal vector of a plane, how does it transform, I have to write different code for that? No, they all have a different form in geometric algebra, and that form is exactly right to make them transform in exactly the correct way using the versors. That is an enormous saving in writing actual code. For the PGA, we just last week got a result from a new program written on in an SSE implementation of the PGA. So that's the 3D Euclidean I wrote outer performs. I always type outer product and so on. Performs the standard LA based. So it's actually the standard straightforward implementation is much less code and actually faster than the optimized previous implementations of Euclidean motions. Right? The structure pays off. But you don't need a full implementation for many things. Steven, our organizer, who has done so much for this get-together, does things at night as well. He programs up Ganja examples in a coffee shop. Know what Ganja means? I didn't. He gives out free samples. Ganja it was geometric algebra, not algebra. Yeah, it's also a Jamaican word for marijuana. That's to get the young kids interested. Many examples in Java, you can change them yourself. They run on your computer in real time, and you'll be amazed what your computer is capable of. So, time to wrap up. That brings us back to Do, or actually to Don't. Linear algebra is just not good enough for geometry. Right? The primitives are only vectors and hyperplanes. Constructions are not at an algebraic level. There's the meet and the join and all these things. To compute intersections, you have to spell them out, or they are as matrix. The column space of the transpose of a matrix of which you have put the contributing vectors as rows, etc. That's not very pleasant, and it involves coordinates. The motions, linear transformations are a bit too general. We don't get this structure, automatic structure preserving that a double-sided project gives. A prefix product doesn't have that property, and that's why you can only apply the matrices to things that are of dimension 1, or you have to make them bigger to work on the composite subspaces. Properties, well, there's often a very nonlinear parameterization where we've seen if we go to the exponential, it's linearly, the rotation is linearly parameterized by the angle phi in a non-redundant manner. If you parameterize it by cosine and sine, which is nonlinear and often redundant because the cosines and sines occur in several places at the time. But you knew that when you went to quaternions. But there's really very strongly developed numerical techniques, decomposition techniques, and so on, and good principles of how you deal with numerical stability. That we don't quite have yet, but as I hope to show with the close relationship with linear algebra, we know in which direction to look, and we're beginning to develop them. But we could sure use some help from mathematicians to do that properly in these algebraic, in the arbitrary spaces. Specification by coordinates, very bad habit. Limited number of geometric primitives. You will never have circles in linear algebra unless you go to this way of looking at it. Structure preservation, you have to enforce it all the time because it's not automatic. You need conditional. You need to see what you're transforming because before you know what matrix you can use. Okay, that leads to conditional things. You don't want that either. And really, quaternions are a cop-out because you're now leaving linear algebra and using something else to do something that's because you were using linear algebra, whereas here they are included for free. And then, by contrast, we believe that geometric algebra is more tailor-made. We have, as primitive, general subspaces, which can really, in the right thing, model planes, lines, spheres, etc., depending on the relationship between the algebra you use to model your reality and the reality itself. Choose that well. There are exceptionless constructions. Intersections always work, even though the answer may not be real. You can still compute on with it, and it always has geometric meaning. Universal motions, by the sandwiching, you can put anything in between and it transforms. You don't have to worry about it. You don't have to decompose it first, compose the element, transform the elements and then recompose them. No, you can just transform the thing immediately. The properties, parameterization is often immediate in terms of the geometric properties. You know, the exponential of a line is a rotation around that line. How much more simple could it be? You know, you'd almost want to, yeah, no, it cannot be simpler, right? But there's some work need to be done in where we are now in making it just as numerically stable as the well thought out implementations of linear algebra are. And that is work that we can probably not quite be trusted to do. We really would need some mathematicians to make sure that we didn't simply generalize. It's so easy to generalize in geometric algebra from a simpler case that we sometimes overdo that in a naive manner. But it becomes a high-level language of geometry. I mean, exponential of a line is a rotator is pretty direct. Structure preservation automatic, completely interrelated set of primitives, you know, and also closed. You never get out of it, and you never want to get out of it. All operations are geometrically meaningful, so if I have a new formula that I think might work, I just type it in, I drag the components around. If it stays together, then it's the formula. If I write it down, I still have to prove it, but I could also just continue because I'm totally confident that it cannot be an accident that it kept together, because the structure would have shown up if I had if I'd moved it even slightly and it broke apart, then it was the wrong thing. It was not what I intended, but still geometrical. Complex numbers and quaternions, you don't need them for geometry. They happen. Numerical GA, need a bit of help. But of course, it's different than what you had in school. So we have tried to write better introductions than I found. I did part of that myself with this book. But for a while, you don't want to do it the old way, and you cannot do it the new way, so you're sort of lost. There are a lot of friends around on various net places. But it is a bit of a time investment, precisely because you will like it so much that you don't want to allow yourself to fall back to your earlier patterns. I gave this talk originally for the applied mathematicians in Brazil, and so there was a little bit of a call of we really would like some help with some of the things, you know. Wish lists, we have some other geometries that we'd really like to have in there. We have these blades, these things spanned with the outer product. That's a very thin manifold in the total possibilities, and that gives you the problem Steven was talking about, that when am I still a subspace numerically? When should I have been a subspace? How do I return to the manifold? If you're interested in these outer product elements, then this is an issue. Same thing with if I estimate a rotor from data, a rotation operator, how do I know it's a rotation operator? With linear algebra, you would do a polar decomposition, forget one of the components, and make sure that you're left with a rotational component. Similar techniques can be done for linear algebra. Geometric algebra, Anthony developed those, but we don't quite know in what sense that would be an optimal solution. In linear algebra, there's strange things like Frobenius norms, which are handy for computation, but geometrically not very meaningful. Can we develop something more meaningful in these spaces? I want to develop a geometric algebra of uncertain geometry, so I don't first have to compute where something is and then have to propagate all the uncertainties in my original data to find out what the uncertainty is, because it has the feeling of being the same operation. So let's make a geometric algebra of uncertain geometry and compute with that. If you're in Clifford algebra, this way of using it was not really known before, and it poses new questions about factorizability and so on that are from a pure mathematics point of view sufficiently interesting, and from us applied people, things that we'd really like to know because we could immediately use them. And don't go off generalizing. Don't make a Clifford algebra over complex numbers or something, or quaternions. Just stick to what we need. I made a little bit of a list for recommended reading, which is of course dangerous. But there are some decent introductory texts. Some of them are beginning to be a bit old to collect your material. They all have their strengths and weaknesses. And there is a journal that I try not to publish in, because it's for the club of geometric algebra people, and like the sphere fitting or the circle fitting, yeah, that just deserves to be known in other fields, so that people get curious about geometric algebra and come to meetings like this and applaud. Okay, so that's the end of the story that I have to tell, as an overview of the components of what we have here and why we like it so much. Okay.